In earlier sections of Chapter 3, we talked about some special subspaces called the null space of a matrix and the range of a matrix. The nullity of A is defined as the dimension of the null space, and the rank of A we're going to define as the dimension of the row space. And we can see that the rank plus the nullity always has to add up to n, the number of columns. And to see that, let's take this example here. This is a 3 by 4 matrix. To find the null space, as in earlier sections, we reduce it down to reduced row echelon form. And the dimension of the null space is the number of arbitrary variables. In this case, there's one arbitrary variable, x3. x1, x2, and x4 can be written in terms of x3. So when you write the solution to ax equals 0 out in vector form, it's just any multiple x3 of this vector here. So this is so the null space of this matrix has dimension 1, and there's a basis for it. All solutions of ax equals 0 or multiples of that. Now the rank is 3 because you can see that when you reduce this down, when you reduce it, you don't change the space spanned by the rows, and the space spanned by the rows is obviously three-dimensional, and here's a basis for it. There are no rows of 0, so if there were, we'd throw those out, and the remaining ones, the non-zero rows, would be a basis. So the rank in this case is 3. It's the number of non-zero rows after you reduce it to row echelon form. And so you can see that the rank is always going to be, the rank plus the nullity will be equal to the number of columns. That is, the nullity, the dimension of the null space, will be the number of unknowns 4 minus the number of special ones here. So rank plus nullity is equal to n, the number of columns, not the number of rows, the number of columns. Now, what's not obvious is that the rank is also the dimension of the range of A. Now, what's the range of A? Well, remember, it's the set of all vectors B such that there exists an A such that AX equals B. Well, AX is just a linear combination of the columns of A, so the range is basically the column space. The range of a matrix is equal to the column space, is the space spanned by the columns. So if you want to know the dimension for the range, you take the columns and put them in as rows, reduce it down to echelon form, and see how many non-zero rows are left, and that will be the number of that will be the column rank, the number of the dimension of the range. So what's not obvious though is that if you reduce A down to row echelon form like this, or if you flip it, take the transpose, find the dimension for the column space by making the columns into rows and reducing that down, they're going to always be the same. There's a theorem on the next page, theorem 10, that states that the rank of A is the same as the rank of A transpose. In other words, the column rank is the same as the row rank. The row rank is the dimension of the space spanned by the rows. The column rank is the dimension of the space spanned by the columns. And it's kind of surprising that they're the same always. They're not even subspaces of the same Rn. The rows are the space spanned by the rows is a subspace of the Rn, where n is the number of columns, whereas the space spanned by the columns is a subspace of Rm, where m is the number of rows. They're all m-dimensional vectors, whereas the rows are n-dimensional vectors, and yet the space spanned by the columns is always equal to the space spanned by the rows. Very surprising result. Well, since the space spanned by the columns is the range, that means the row rank of A is the same as the range. Okay, so probably confused you a little here, but let me review one more time then. The nullity is the dimension of the null space. the rank is the dimension of the row space, but it's also equal to the dimension of the column space and therefore the dimension of the range. So nullity plus rank equals n, the number of columns. Okay, let's look at the homework for section 3.5. First two problems ask if the given set of vectors forms a basis for R2, and you can throw out immediately if the set has only one vector, it can't possibly be a basis. If all bases of R2 have to have two vectors exactly, and the two vectors have to be independent. So if you have three vectors, can't be a basis. One vector because they can't be independent. One vector can't be a basis because it can't span the space. Two vectors may or may not be a basis depending on whether they're independent. And this is similar, except let's see if it spans R3, if it's a basis for R3. Then there's some problems where you're supposed to find the a basis for the null space, and you just solve AX equals 0 that we did in chapter 1 and see how many vectors there are in the vector representation that will be equal to the number of arbitrary variables. These two problems say find a basis for the range of A. Well, remember the range is exactly the column space. It's the space spanned by the columns. So you just take the columns and put them in as the rows of the matrix, the transpose, and reduce that down and see how many non-zero rows you have left, and the non-zero rows will be a basis for the column space because the rows are the columns of the original matrix. In fact, you could reduce this down without flipping it, without taking the transpose, and that would tell you the rank because the row space and the column space have the same dimension. However, they don't have the same basis because they're not the same space, but they have the same dimension. Problem 33 says, what is the largest possible value for the rank of A? If A is 3 by 3, well, see, the rank cannot, since the rank is the dimension of the column space and the dimension of the row space, it can't be more than the number of rows, and it can't be more than the number of columns. So the rank can't be ever more than the minimum of the number of rows and the number of columns. So it's the rank is always less than or equal to the minimum of M and N.